Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is an exergonic reaction? Okay, so an exergonic reaction this is a chemical reaction where the energy is exiting and a way to remember that energy is exiting is because exergonic and exiting, they both start with EX. So that's a way that you can remember that energy is exiting in an exergonic reaction. And it is exiting the system. Exergonic reactions are also known as spontaneous. So spontaneous reactions mean that they occur without the addition of energy. So we know that a reaction is spontaneous when its Gibbs free energy value, so when delta G, is negative. When delta G is negative, this means that our reactants have more free energy than our products. Okay, so these are some of the characteristics of an exergonic reaction, and we can also draw a graph of energy versus time to show the reaction and how much energy is produced or released as the time of the reaction goes through. So typically, an exergonic reaction graph kind of looks like this. So here is where we start off, our reactants, and they have a higher energy than our products. And then we can show delta G. Right here. Delta G, and it is less than 0. So that means that it is negative. And we can also say that energy was removed. So you can see our reactants are at a much higher energy than our products. And this is the characteristics of an exergonic reaction. So now let's see the opposite of an exergonic reaction, which is an endergonic reaction. So endergonic reaction, again, it is a chemical reaction. But this time, energy is added. Energy must be added before our reaction can proceed. Okay, so an endergonic reaction is known as non-spontaneous. And that's because it doesn't just occur because we need energy in order for it to occur. And also, for endergonic reactions, our delta G value is positive. So this means our reactants have less free energy than our products. Okay, so now let's compare an endergonic's reaction diagram. So again, we're going to plot energy versus the time. And the energy of our reactants starts off low. And then as the energy progresses, our products have a higher energy. So this is our reactants. This is our products. And again, we can show delta G. And this time delta G is positive. So delta G is greater than 0. And energy is added. Okay, so these are the definitions for both exergonic and endergonic reactions. So the junior tutor said that an exergonic reaction is a type of chemical reaction wherein energy is released. This means that the change in free energy is negative and that the reaction is spontaneous at the right conditions. Yep, so this solution is correct. Okay, so question number 2. How many valence electrons does nitrogen contain? Okay, so first let's look up nitrogen on the periodic table to find out its atomic number. So nitrogen is found here, and it has an atomic number equal to 7. So what the atomic number tells us is the number of protons. So this means that nitrogen has 7 protons. If we were to have a neutral nitrogen atom, this means that in order to have a neutral atom, we need to have the same number of electrons as we do protons. So therefore, for a neutral nitrogen atom, there are also 7 electrons. And these are 7 electrons in total. So if we draw the electron dot diagram of a nitrogen atom, we start off with the inner electrons, which are only 2 in the s orbital. And then we draw the remaining electrons in the next shell. So we already drew 2, so we just need to draw 5 more. 1, 2, 3, 4, 5. So therefore, nitrogen has 5 valence electrons. So valence electrons are the electrons that are found on the outermost shell of nitrogen. So if we count it out, we can see that nitrogen has 5. So let's see what the junior tutor said. The electrons of an atom or an element consist of 2, valence and core electrons. Valence electrons occupy the outermost shell, or the highest energy level of an atom, and can participate in the formation of chemical bonding. On the other hand, core electrons occupy the innermost shell, or the lowest energy levels of an atom, hence cannot participate in the formation of chemical bonding. While these electrons are not involved in the bonding, they affect the chemical reactivity of an atom. For the core and valence electrons in nitrogen, we start off by writing the electron configuration of, I think they mean nitrogen, with 7 electrons. The highest energy level is n equals 2. We have 2 subshells occupied with electrons on this energy level, 2s2 and 2p3. Because of this, nitrogen will have a total of 5 valence electrons. Yep, so this solution is correct. Okay, so question number 3. Which of the following grouping represents isoelectronic species? Okay, so let's define the term isoelectronic species. When we have isoelectronic species, this means that they are species that have the same electron configuration. So they can be a combination of atoms, or not atoms, but ions, and like a ground state atom that have the same electron configuration. So to answer this question, they give us a different variety of like ions and or also like an atom in its ground state. And what we need to do is find out all of their electron configurations and then see which ones give same configuration. So let's do the first example. For part A, we have N3-, F-, and sodium plus. So let's look at our nitrogen that has a 3- charge. And the first thing I like to do is find the electron configuration of just a nitrogen in its ground state configuration first. So when we find electron configuration, we first want to divide our periodic table into the different sections, different orbital sections. So the first two columns are our s orbital. This green box is our p orbital. And then the middle, so the transition metals, are the d orbital. And lastly, the f orbital are the last two rows, so the lanthanides and actinides. So starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter. But once we get to the d orbital, we write the row number -1, so you can see that in row 4, it's still 3d. And when we get to the f orbital, it's the row number -2. Okay, so let's do nitrogen's, ground state nitrogen's electron configuration first. So starting from hydrogen, we write 1s, and then the superscript of 2 tells us how many electrons are in that orbital. So when we have 1s2, this is the same electron configuration as helium. Now we move on to the next row, 2s2, and then moving over to the p orbital, we write 2p, and then count up to the nitrogen. So 1, 2, 3, 2p3. So this is the electron configuration of a ground state nitrogen atom. But for the question, we want to know the electron configuration of N3-. So when something has a negative charge, this means that electrons are added. So in this case, 3 electrons are added. So this affects our electron configuration because instead of 2p3, we now have an extra 3 electrons. So we can write the new electron configuration as 1s2, 2s2, and then 2p6. So this is now the electron configuration of N3-. So now let's find the electron configuration of a ground state fluorine atom. So for fluorine, it is found here, atomic number 9. And we just write 1s2, 2s2. And for fluorine, it's 1, 2, 3, 4, 5. So 2p5. Okay, so now we want to know the electron configuration when fluorine gains an extra electron. So we would write it as 1s2, 2s2, and then 2p6. So you can see that N3- and F-, they both have the same electron configuration. So these are already isoelectronic, but let's see the last ion, which is sodium plus, to see if it matches the electron configuration of our other two ions. So first, let's find the ground state electron configuration of a sodium atom. Starting from hydrogen, it's 1s2, and then 2s2, 2p6, and then sodium is found right here, atomic number 11, so we write 3s1. Now this is the electron configuration of a ground state sodium ion, but when we have sodium plus, this means that one of the electrons was removed. So now we can write the new electron configuration, and you can see it has the same electron configuration as our other two ions. So therefore we can say that these are isoelectronic species. Okay, so I guess we already solved the question, but we can double check and do like the second part. Let's do B just to see if it is incorrect. So we have beryllium, just a ground state beryllium atom, and its electron configuration. So beryllium is found here, atomic number 4. It would just be 1s2 and then 2s2, and then it ends there. And now the next is an ion, so it's aluminum, and then aluminum 3+. So aluminum is found here, atomic number 13, and its ground state electron configuration is 1s2, 2s2, 2p6, 3s2, and then 3p1. If it were to lose 3 electrons, then it would have the electron configuration 1s2, 2s2, 2p6. So already we see that it's different from the beryllium. And then we can just do our last ion, which is chlorine and Cl-. Okay, for a ground state chlorine atom, it is found here, atomic number 17, and its electron configuration is 1s2, 2s2, 2p6, 3s2, and then 3p5. And if it were to gain an extra electron, then it would end in 3p6. Okay, so already we can see that these 3 options are not isoelectronic. Okay, so this kind of verifies that the correct answer is A. And we can see what the junior tutor said. Isoelectronic species are ions or atoms that have the same electronic configuration. Step 1 is to write the electronic configuration of each ion or atom for each grouping. You can see they did all the individual electron configurations, and option A gave us isoelectronic species. This was option B, which were all different. And if we were to do option C and option D, you can see that all of their electron configurations would all be different as well. So step 2, determine groupings that have the same electronic configuration. And they found that it was option A. So this solution is correct. Okay, so on to question number 4. "30 grams of glucose, which is C6H12O6, has a molar mass of 180.16 grams per mole, is dissolved in 100 grams of water, which has a molar mass 18.02 grams per mole. What is the mole fraction of water in solution? Note that glucose is a non-volatile solute." Okay, so first let's define what a mole fraction is. So a mole fraction can be denoted as X of a I, and it tells us the moles of a component. So in this case, let's say component I divided, divided by the total amount of moles in the mixture. Okay, so for this question, we want to know the mole fraction of water in a solution of the 30 grams of glucose and 100 grams of water. So we can write out the equation for mole fraction. So mole fraction X is equal to N over N total, where N is the amount of a constituent in moles. And as you can guess, N tot is the total amount of moles. Okay, so let's break up this solution into different steps. So step 1 would just be to find the number of moles of both glucose and water. Okay, so let's recall that the equation for finding the number of moles is just mass over molar mass. Okay, so first let's find the number of moles of glucose. So we have 30 grams of glucose, And they gave us the molar mass of glucose, which is 180.16 grams per mole. So if we divide the two, we get number of moles of 0.17. Okay, so now let's find the number of moles of water. So we have 100 grams of water, and we know the molar mass of water is 18.02 grams per mole. So 100 divided by 18.02 is 5.55 moles. Okay, so step 2 is to find N total. So N total is just equal to 0.17 moles, which is the number of moles of glucose, plus the number of moles of water, which is 5.55, and we get N total equal to 5.72. And finally, we have everything we need to calculate the mole fraction of water. So X, water, is equal to the number of moles of water, which was 5.55, and we divide this by the N total, which is 5.72. So 5.55 divided by 5.72 is 0.97. So this means the mole fraction of water is 0.97. And if we were to convert this to a percentage, then that means that 97% of this solution is water. And the junior tutor said that glucose is described as a non-volatile solute, meaning that no parts of the solute will escape from the solution. The mole fraction of a component in a solution can be solved using the equation. Okay, so they showed how the denominator is the sum of the number of moles of the components of the solution. And in this problem, we only have two components, which are glucose and water. We need to get the number of moles present given their mass. This can be calculated using the equation. Number of moles is equal to mass over molar mass. So they have both of the moles of the two components, and then they calculated the mole fraction of water and also got 0.97. So the solution is correct. Okay, so on to question number 5. What makes the molecule SO3 nonpolar? So this is question number 5, yep. So to answer this question, let's first find the Lewis structure of SO3. So to do that, let's calculate the total number of valence electrons for a molecule SO3. Sulfur has 6 valence electrons, and oxygen also contains 6, and there are 3 oxygen atoms, so we multiply this by 3. which gives us a total of 24 valence electrons. So now we can draw sulfur as our central atom, and then draw 3 oxygen atoms symmetrically around it. And all of these oxygen atoms will have a double bond. And we can draw in all of the lone pairs on the oxygen. And sulfur is one of those atoms that is able to create multiple bonds. So in this case, there are like 6 bonds to the sulfur. And now let's find out its VSEPR shape. So let me look up a VSEPR table. Okay. And if we analyze our Lewis structure, then we can see that this structure contains 0 lone pairs on our sulfur atom and 3 bonded atoms. So using our VSEPR chart, we can see that this corresponds to a trigonal planar molecular shape and electron geometry. So I'm just going to write trigonal planar. And you can see that this atom is also symmetrical. So now let's look up the electronegativity values of the atoms that are involved. So to find out whether or not an atom is polar or nonpolar, we want to find out the difference in electronegativity between the 2 atoms involved in the bonding. So in this case, we want to know the electronegativity difference between a sulfur atom and an oxygen atom. So the electronegativity of oxygen is 3.5, and the electronegativity of sulfur is 2.5. So this gives us an electronegativity difference of 1. So this tells us that the bond is polar, because our electronegativity difference is greater than 0.4, but less than 1.69. Okay, so we know that a sulfur and oxygen bond is polar, but if we look at our molecule, you'll see that all the dipole moments that point towards the direction of oxygen cancel each other out. So therefore, the SO3 molecule is nonpolar. And this is because the dipole moments cancel each other out. So we can compare the SO3 molecule with a molecule of SO2. If we were to find the total valence electrons of an SO2 molecule, again, sulfur has 6, oxygen also has 6, but this time there are 2 atoms of oxygen. And then we have a total of 18 valence electrons. And if we were to draw sulfur again as our central atom, and 2 double bonded oxygens, if we count out the number of electrons I have so far, I only have 16, so the remaining 2 will be a lone pair on the sulfur atom. So let's find out its Vesper shape. So this time our sulfur atom has 1 lone pair and 2 bonded atoms. So if we find out its Vesper shape, this tells us that when we have 1 lone pair, 2 bonded atoms, we have a bent molecular shape. And if we were to draw the same dipole moments going towards the direction of oxygen, since oxygen is more electronegative than our sulfur, then you can see that there is a net dipole moment going towards the oxygens. So this time, they aren't cancelled out, and therefore we can say that this molecule is polar. Is polar due to its structure and it has an overall non-zero dipole moment. Okay, so this is comparing SO3 and SO2 and why our SO3 molecule is nonpolar, whereas our SO2 molecule is polar. Okay, so the junior tutor said that the Lewis structure can give us an insight into whether a molecule is polar or nonpolar. For the molecule SO3, the sulfur atom will act as a central atom for the molecule with 3 oxygen atoms attached to it. There are a total of 24 electrons present, hence the Lewis structure of the molecule is written as... Okay, so this Lewis structure is actually incorrect because if we were to count out all the electrons in this structure, each bond containing 2 electrons, we have a total of 26. So this is actually the Lewis structure of SO3 2-, which is known as the sulfate ion. And you can see that the SO3 2-, sulfite ion, sorry. So this is the sulfite ion, and you can see that the 2 single bonded oxygens would give off a minus charge each, and this gives us 26 valence electrons. Then they said that it's trigonal planar, resulting in a 0 dipole moment. So the explanation is correct, but it doesn't really make sense with the Lewis structure that they drew. So let me just say that Okay, so I said the SO3 molecule is indeed nonpolar because it has a trigonal planar electron geometry and molecular geometry, with the dipole moments canceling each other out. However, the Lewis structure drawn is incorrect. There are 26 electrons in the structure, with the 2 single bonded oxygens containing a negative charge each. This is the Lewis structure of SO3 2-, which is the sulfite ion. Okay, so I'm going to say that this solution is incorrect, just because the Lewis structure is incorrect as well. And now we can move on to question number 6. How many valence electrons does the phosphorus atom have? Its group number is 5A and atomic number is 15. So we know that phosphorus has atomic number equal to 15. So this means that there are 15 protons in phosphorus, and therefore if we had a neutral phosphorus atom, then we also have 15 electrons. And this is so that the negative charge can cancel out the positive charge from the 15 protons to give us a neutral atom. Okay, so now let's draw the electron diagram and show the 15 electrons for a phosphorus atom. So the first 2 would be in the inner shell, so the 1s orbital. And then the next shell can house 8 electrons. So let me draw them in. Okay, so if we count out all these electrons, I've only drawn 10 out of the 15. So we need to have another shell. And we can draw 5 more electrons. Okay, so this is a phosphorus atom. And therefore, we have 5 valence electrons. So the valence electrons, these are the electrons that are found in the outermost shell. And in the case of phosphorus, it is these 5 right here. The junior tutor said that valence electrons are the electrons that can be found in the outermost shell of an atom and occupy the highest principal energy level of an atom. To determine the number of valence electrons, see this table for reference. So they kind of summarized the different trends you see depending on what group you're in the periodic table. So for example, group 1, alkali metals, have 1 valence electron. Group 2 has 2 valence electrons. And groups 3 to 12, which are the transition metals, it kind of varies. So they have a note here that says the general method for counting valence electrons is generally not useful for transition metals. Instead, the modified d electron count method is used. For group 13, they have 3 valence electrons. Group 14 has 4, 15 has 5. So this is where our phosphorus atom lies. Group 16 has 6 valence electrons. Group 17 has 7. And noble gas has 8, with the exception of helium, which only has 2. Phosphorus is in the group 5A. Therefore, it has 5 valence electrons. Okay, so the solution is correct. Okay, so question number 7. What is /R the spectator ions in this reaction? Okay, so first let's define what a spectator ion is. Spectator ions. So spectator ions, they do not participate in the reaction. And we can find out which are the spectator ions because they appear on both the products and the reactant side. Okay, so now let's try to find out the spectator ions in this reaction. So they have the full molecular reaction shown. So let me also write it out. The molecular equation, HC2H3O2 aqueous plus sodium hydroxide I believe this is the acetate ion. So this is sodium acetate plus H2O. Okay, so after we write out our molecular equation, which is the full equation showing all of the species in their molecular forms or in their molecule forms, and after we write the molecular equation, we want to write our full ionic equation. So to write the ionic equation, basically everything that is in the aqueous phase, we write as separate ions. So the only things that don't separate into the ions would be like our pure liquids or pure solids. So in the case of this example, our H2O is in a liquid form, so it's going to be the only thing that doesn't separate into its ions. So now we can just write all of the other species that are in the aqueous form as ions. So breaking up our first compound would be H plus the acetate ion and then breaking up sodium hydroxide into its ions, Na plus aqueous plus OH minus Then let me write all of our products down here because there's no room. We have another sodium ion plus another acetate ion. And now water is the only one that stays the same. So it's H2O liquid. Okay, so after we write down the full ionic equation, we want to now write out our net ionic equation. So this is when we would cancel out the spectator ions that appear on both the products and the reactant side. So in this case, we can cross out this ion, and we can cross out the sodium ion, which leaves us with our net ionic equation, which is H plus aqueous plus OH minus aqueous produces H2O liquid. So therefore, for this reaction, sodium plus and C2H3O2 minus are the spectator ions. So they're called spectator ions because it's as if they're like watching the reaction happening. They don't actually participate in the actual reaction. That's how it kind of got its name. And if we look at the options they give us in the question, we can see that this is option D. The rest, this only no. Yep, and then H plus and the OH minus are the ions participating in the reaction. So we know that that's incorrect, so our correct answer is D. And the junior tutor said that spectator ions are ions that do not undergo any chemical change in a reaction. It is found in the solution before and after the reaction. This problem, the reaction equation is the following. And when dissociation happens, the equation becomes the following. So I think they forgot to write this part in its ionic form. But still, they saw that Na plus C2H3O2 minus did not change at all. They are found in the solution before and after the reaction. Therefore, they are the spectator ions. So this solution is correct. I'm just going to add in brackets because I think they just forgot to write the dissociation. Okay, so I think they meant to say that. But this solution is still correct. Okay, so question number 8 is to write the chemical formula for magnesium fluoride. Okay, so first let's see what type of compound we have. We have magnesium, which is a metal, and we have fluoride, which is a nonmetal. Therefore, we know that this is an ionic compound. And we can also break up magnesium fluoride and draw out the two ions that form this compound. So magnesium, well, first we'll show that fluorine we know is F minus, and magnesium is Mg2 plus. So if we crisscross our charges, we get a final chemical formula of MgF2. And we know this because in order to get a neutral compound, we need 2 fluorine atoms to neutralize the positive 2 charge from our magnesium. So this is why the chemical formula is MgF2. So now let's see what the junior tutor said. They said in writing the chemical formula of an ionic compound, the elemental symbol of the cation is written first, followed by the elemental symbol of the anion. Moreover, the charge of the cation becomes the subscript of the anion and vice versa. Magnesium fluoride is an ionic compound composed of the cation Mg2+ and anion F- with the chemical formula MgF2. Yep, so this solution is correct. Okay, so question number 9. Is xenon tetrafluoride polar or nonpolar? Explain your answer. Okay, so to find out whether or not a molecule is polar or nonpolar, we first need to draw out its Lewis structure. So the steps for writing a Lewis structure is to first find out the total number of valence electrons. In the case of xenon, xenon has 8 valence electrons, and fluorine has 7 valence electrons. There are 4 fluorine atoms in xenon tetrafluoride, so we multiply this by 4. And then when we add these values up, we get a total of 36 valence electrons. So now let's try to draw out the skeletal structure by drawing our xenon as our central atom. And then we kind of just draw the 4 fluorine atoms symmetrically around it. And we can show all of their lone pairs. Okay, so if we count out how many electrons I've drawn so far, with each bond containing 2 bonding electrons, then we only have 32 electrons in this structure, and I need 36 in total. So for the remaining 4 electrons, I'm just going to draw them as lone pairs on our xenon. Okay, so this is our final Lewis structure. And if we want to analyze its molecular shape, let's first count out the lone pairs and bonded atoms of our xenon atom. There are 2 lone pairs in total. And the xenon is bonded to 4 atoms. So we have 4 bonded atoms. So now let's use a Vesper chart to find out the type of molecular shape we have. So we have 2 lone pairs and 4 bonded atoms. So this is on the next page. So when we have 2 lone pairs and 4 bonded atoms, we have a square planar molecular shape. Okay, so we know the molecular shape. And now let's find out whether or not a xenon-fluorine bond is polar or nonpolar. So to do that, we need to calculate the electronegativity difference between xenon and fluorine. So now let's look up the electronegativity values. So xenon is 2.6 and fluorine is 4. So this has an electronegativity difference of 1.4. So therefore we can say this bond is polar. Xenon-fluorine bond is polar. And we know that because its electronegativity difference is greater than 0.4 but less than 1.67. So now we can show dipole moments pointing towards the direction of the fluorines, since fluorine is noticeably more electronegative than our xenon and creates these dipole moments. But if we look at the shape of our molecule, which is square planar, you can see that these dipole moments cancel each other out. So we can say that xenon tetrafluoride is a nonpolar molecule. So this is an example of how we can have a polar bond, but an overall nonpolar molecule. This is because the dipole moments cancel each other out. Due to the symmetrical molecular shape. And we can say up here that we have net dipole moment is 0. Okay, so the junior tutor said that a covalent bond is formed when two atoms share electrons. And there is equal sharing of the bond electrons, the electronegativities of the two atoms become equal, leading to the formation of nonpolar covalent bonds. The Lewis structure of xenon tetrafluoride shows that the molecule has a symmetric structure, therefore, dipole moment will cancel each other out, resulting in a nonpolar molecule. Okay, so they kind of talked about nonpolar covalent bonds, but xenon and fluorine is a polar bond, so I'm not sure why they just mentioned it. But the answer is still correct. And then I'll just kind of specify why. Okay, so I said the solution is correct. Even though the xenon-fluorine bond is polar, the overall molecule is nonpolar because the dipole moments cancel each other out due to the symmetrical molecular shape. Okay, so question number 10. Is to write the full electron configuration of fluorine, atomic symbol F, and then write the full electron configuration of a fluoride ion, which is F minus. How many valence electrons does a neutral fluorine atom have? Okay, so first let's write the electron configuration of fluorine. And the first step of writing electron configurations is to divide our periodic table into the different blocks. So we divide it into the S block, which is these first two columns, including the helium. And the P block is shown here in green. The D block is our transition metals in orange, and the F block are the bottom two rows, which are the lactanides and actinides. So when we write the electron configuration, we start from hydrogen, which is 1s, and then we move left to right across the periodic table, also showing the superscripts, which tells us how many electrons are in that orbital. So for example, for hydrogen and helium, this is 1s2. And then on to the next row, we have 2s2. And then moving across to the 2p orbital, we have 2p. And then we count out up to the fluorine how many electrons would be in this orbital. For a fluorine atom, we have 1, 2, 3, 4, 5. Okay, so 1s2, 2s2, 2p5 is the full electron configuration of a ground state fluorine atom. And now the question says to write the full electron configuration of a fluoride ion, so F minus. So the difference between F and F minus is that the fluoride ion now has an extra electron. This is why it has a negative charge. So when we have an extra electron, we can write our new electron configuration, which is 1s2, 2s2, and then 2p6. Okay, so you can see that it now has the same electron configuration as neon. So we can show neon in square brackets, kind of show that it's the same electron configuration as F minus, meaning that these two are isoelectronic. So now the third part of the question asks, how many valence electrons does a neutral fluorine atom have? So neutral fluorine in total has 9 electrons. So if we count out all of the superscripts in our neutral fluorine atom, 5 plus 2 plus 2 is 9. So now let's try to show a diagram of this atom. So when we have a fluorine atom, we have 2 electrons in the innermost shell. So this is the 1s2 orbital. And then in the next shell, we draw the remaining 7. So therefore, we can say there are 7 electrons, or 7 valence electrons. So valence electrons refers to the electrons in the outermost shell, and you can see that it is the 7 that are shown here. So the junior tutor said that the electron configuration of an atom represents the arrangements of electron distribution among the orbital shells and subshells. It is used to determine the shape and energy of electrons in an atom. To write the electron configuration, follow the steps below. From the periodic table of elements, determine the atomic number. 2. Determine the charge of the atom. If it's neutral, there'll be no additional electrons. If it's cation, which is positively charged, then the coefficient of the charge represents the number of electrons lost. If it's an anion, the coefficient of the charge represents the number of electrons gained. Write the electron configuration, taking table below as a reference. Okay, so this is a helpful table to help write the electron configuration, and they just kind of summed up all the different sublevels and how many electrons will be found in each orbital. So for part A, they got 1s2, 2s2, 2p5 for neutral fluorine. And when we have a fluoride ion, which has a -1 charge, 1 electron was added, and they got 1s2, 2s2, 2p6. For part C, valence electrons are the electrons that can be found in the outermost shell of an atom and occupy the highest principal energy level of an atom. It can be identified by just counting the number of electrons, represented by the superscript, of the last principal energy level. For the electron configuration of a neutral fluorine atom, it has 7 valence electrons. Yep, so this solution is correct. Okay, so question number 11. What are core electrons? Core electrons. This means that these are the electrons that are not in the outermost shell. And they also do not participate in bonding. However, core electrons can still affect an atom's reactivity. So for example, when we have more core electrons, this means we have a larger atomic radius. And this also tells us that our valence electrons, which are the electrons in the outermost shell, they are further away . So they are further from the positively charged nucleus. So this means that these valence electrons have a less effective nuclear charge. And they can also be easily lost. Okay, so the junior tutor said that Electrons fall into two categories, valence electrons and core electrons. Basically, valence electrons occupy the outermost shell, where all the reactions and exchanges of electrons occur, while core electrons are found at the innermost shell. They're usually not involved in bonding, but have a great influence on the chemical reactivity of an atom. Yep, so this solution is correct. And then I'm also just going to add what I said as well. When we have more core electrons, we have a larger atomic radius. Valence electrons would then be further away. The positively charged nucleus. Giving a less effective nuclear charge. Also known as Zeph. And easily lost valence electrons. Okay, so question number 12. What is the electron geometry of C2H2? So first let's write out its Lewis structure. And in doing so, we need to calculate the total number of valence electrons. So carbon contains 4 valence electrons, and there are 2 carbon atoms, so we multiply this by 2. Hydrogen contains 1 valence electron, and we also multiply this by 2. Give us a total of 10 valence electrons in C2H2. So now let's draw our 2 carbon atoms bonded together. And then each of these carbons will contain 1 single bonded hydrogen. So now if we look at our carbon atoms, you'll see that they don't have a full octet yet. So we know that these 2 carbon atoms will be triple bonded. And we can double check and count out how many electrons I've drawn in this structure. Each bond contains 2 bonding electrons. So we have 10 electrons in this Lewis structure, so we know that it is correct. So now let's analyze this Lewis structure and look at one of the central carbon atoms. And you can see that both of the carbon atoms have 0 lone pairs. And each carbon atom has 2 bonded atoms. If we look at the VSEPR chart, we can see that if we have 0 lone pairs and 2 bonded atoms, this means that we have a linear molecular shape. The carbons are sp hybridized, and the bond angles are 180 degrees. So you can kind of already see here how these bond angles are 180 degrees. Yep, and electron geometry is also linear. So linear molecular shape and electron geometry. Okay, so the junior tutor said that to determine the molecular geometry of C2H2, also known as ethine, we did need to determine first its Lewis structure. In order to find the Lewis structure, we need to determine the total valence electrons participating in the bond formation. So they got 10. And after finding the total valence electrons, pick the least electronegative atom, and that would be the central atom. So this is an exception where the least electronegative atom is hydrogen, but since hydrogen can only form one bond, then we know that carbon would be our central atom. And then finally complete the total valence electrons by placing lone pairs on atoms with an incomplete octet. So we didn't need to do that because we just formed a triple bond between the carbons. Carbon atoms have 2 electron bonding groups, which correspond to a bent structure. So this solution is incorrect. Central, or the carbon atoms, contain 0 lone pairs and 2 bonded atoms each. Therefore, the molecular geometry and electron geometry would be linear. Okay, so I think the junior tutor corresponded it to a bent structure. If we were to have 2 bonded atoms and 1 lone pair, then indeed we would get a molecular shape that is bent. But since the carbons don't have any lone pairs, then we just have a linear molecular geometry. Okay, so I think we have time for one more quick question, which is, what is the molecular geometry of carbon tetrachloride? So first we need to draw out the Lewis structure of this molecule, and we just need to count out the total number of valence electrons. So for carbon, there are 4 valence electrons, and chlorine contains 7. And since there are 4 chlorine atoms, we multiply this by 4. And if we add this up, we get total number of valence electrons equal to 32. So now let's try to draw out the skeletal structure. We'll have carbon as our central atom. And then I'm just going to draw my 4 chlorine atoms symmetrically all around it. And then I'm going to draw in all of my lone pairs on the chlorine atoms as well. Okay, so each bond contains 2 bonding electrons. And if I were to count out how many electrons I've drawn so far in this structure, then you can see I already have 32 electrons drawn. So each bond contains 2 electrons, and each chlorine has 6 valence electrons, or 6 electrons that are non-bonding. So now let's analyze this Lewis structure to find out its molecular shape. So the central carbon atom contains 0 lone pairs and 4 bonded atoms, which are the 4 chlorines. So if we look at our VSEPR chart, we'll see that when we have 0 lone pairs and 4 bonded atoms, this tells us that we have a tetrahedral molecular shape. and also a tetrahedral electron geometry. Our carbon is sp3 hybridized, and the bond angles are 109.5 degrees. Okay, so the junior tutor said 32, and they have the correct Lewis structure, but they didn't say which one of these is the molecular geometry, which should be tetrahedral. So this Lewis structure is correct. Okay, so therefore option A. Okay, so let's just answer this last question. Part A, using the following equation, lead sulfate plus 4 lithium nitrate makes lead nitrate plus 2 lithium sulfate. How many moles of lithium nitrate will be needed to make... Wait, how many moles of lithium nitrate will be needed to make... I'm guessing lithium sulfate, assuming you have an adequate amount of lead sulfate to do the reaction. And then we would just need to see how many moles. So we can see that we need 4 moles of lithium nitrate needed to produce lithium sulfate. Okay, so we need 4 moles over 2. I think this question was supposed to ask how many are needed to make 3 moles of lithium sulfate. But I think it was just written wrong. So if we need three moles of lithium sulfate produced, then this is when we would just use the molar ratios. So we write 3 moles of lithium sulfate and then multiply by the molar ratio, which is 2. Four moles Okay, so 3 times 4 is 12 divided by 2. So 6 moles of lithium nitrate is needed. That's what I had in my notes, so I think the question just came out wrong. And we can do a similar question, which is the next equation. 2 moles of water produces 2 H2 gas plus 1 oxygen gas. Now it asks how many moles of oxygen gas are produced if you have 0.8 moles of lead. So now I think they mean 0.8 moles of water. So I'm just going to say if we have 0.8 moles of water, then again we would just use the molar ratios to solve this question. So we multiply 0.8 by 1 mole of oxygen requires 2 moles of water. So 0.8 divided by 2. So you get 0.4 moles of O2 is produced. Okay, so the junior tutor said, using the following equation, 3 moles of lithium sulfate is produced. Or sorry, 6 moles is needed to make 3 moles of lithium sulfate. Yeah, I think all of the images are kind of in a different order. But you need 6 moles of lithium nitrate and 0.4 moles of oxygen. Then I'll just say the images may be in a different order. Okay, so those are all the questions for today's session. If you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a like and a comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.